Hey, this next video is going to be about what are called frequency polygons or distribution polygons. And there's three different kinds I want to show you. We first have what's called a frequency distribution. And I'm going to compare that to a cumulative frequency distribution and also a probability distribution. So they're going to look similar, but they're all different. So a frequency distribution means that you are recording the frequencies of how often something occurs. That means the actual count, the actual number. So I made a graph here of the number of people and their ages, and I put them into a histogram because ages are continuous, which means nobody is exactly any given age. So we're going to have these intervals of ages from 0 to 10, 10 to 20, 20 to 30, to 40, and to 50. So all the people that are in this range, there's 5 of them, and from 10 to 20, there's 10 people. From 20 to 30, there's 10, 30, 40, 15, and so on. So that is what's called a frequency distribution. I'm just literally counting. Each of these bars represents the actual count. Okay, now a cumulative frequency distribution, I'm actually going to use the same one to show you what it looks like, but a cumulative frequency distribution now along the side is not the individual counts, but it becomes a cumulative amount. Here's what I mean. We are going to redraw this graph because on this graph, I only had the total go up to 30. But if I add up all of these bars, 20, 15, 10, 10, 5, it adds up to 60. And so I need the side of my graph to go all the way up to 60 instead, like this one. Okay, so I'm just going to redraw this exact graph. So first I just had at 5, and then at 10, I had 2 bars at 10, and then one at 15, and then one going up to 20. Okay, so now when I made this new graph, it looks exactly the same. It's just shorter, really. It should just be shorter. And I didn't get out a ruler and measure these or anything, but this is still supposed to be 5, 10, 10, 15, and 20. But because this now goes up to 60 instead of only up to 30, this is squished more. Okay, so now when we make our cumulative frequency, we're going to put a dot at the center of the interval. So that dot right there represents that there are 5 people who are between 0 and 10 years old. And then between 10 and 20, there were 10 people, but now we're doing a cumulative. So if this was 5, I'm going to put these actual counts in here so we know what to be adding. So now if there were 5 here plus 10 is 15, now this dot is going to go at 15. And then the next one adds on 10 more, which is now at 25. So now this dot's going to go at 25. And then this dot, add on the 25 to 15, that's now 40. And so now I put that dot at 40. And then I add on 20 more and I get up to the 60 and I put that dot at 60. And then I connect these. And that is called my cumulative frequency distribution, or my cumulative frequency polygon. I know it's just kind of weird. I mean, I don't ever use these cumulative ones, but it's something I have to teach you. So these we'll see a lot. These regular frequency distributions, that's just a regular histogram, which we'll talk a lot more in Unit 2. But here, when you do the cumulative, remember you put your first dot at the center of the bar, and then you start adding. 5 plus 10 is 15, plus 10 is 25, plus 15 is 40, plus 20 is 60, and this line is a cumulative frequency distribution. Okay, now a probability distribution is once again similar. This graph looks the same again, but this time the numbers that I have on here are percentages or probabilities instead of frequencies or counts. So I took my 5 people out of my 60 and divided 5 divided by 60, and I got 0.08. So I renumbered this from 20% up to 100% because percents have to go up to 100 or 1.0. So I have 0.20, 40, 60, 80, 100. Remember the first graph I just counted by fives because I was doing the count. The second one I had to have it go up to 60 because the total was 60. So I had to have my bars go up to 60 here. My cumulative here, I'm doing a percent. So these are now decimals, and this is 100% or 1.0. So my first bar, 5 out of 60 was 8%. Then 10 out of 60 was 16.7%. So I rounded it to 17. The next one was still 17. And then this one was 15 divided by 60 is 25%. And the last one was 33%. So this is exactly the same as my first one, my frequency distribution, only instead of counts, I have calculated these as percentages. Okay, so those are all very similar, but yet distinctly different, and they're all going to be important. So that's those three graphs, excuse me here. And let me talk more about this probability. I'm trying to grab my graph, sorry. Probability density curve, because this is the one that we're going to see a lot of. You know it as what's called a normal curve. Okay, we'll get to that in a second. But the key things about a probability density curve is that the area under the curve has to equal 1. Like in my last one, I added up all those bars, the 0.08 and the 0.17 and so on, and those added up to 100%. So the area underneath all those bars have to add up to 100%. Okay. Now, the probability of any exact value is 0. That seems weird, but if I said, what is the probability of 5 in this graph right here? It's actually 0, which is kind of weird because I do have somebody who is in this bar between 0 and 10 years old. I have 0.08% or 8% of the people are in this bar. But yet if I say what percent of the people are 5 years old, I have to say 0. And the reason is because all the numbers in here are continuous, which we've talked about what that means. So it just means that 8% of these people are in this bar, but any particular number is going to be 0. It seems odd, but that's what it is. Okay, so that'll make a lot more sense as we go on too, because this is just the beginning of this concept. And so as we develop the things of a normal curve, all of that will make more sense. So right now I'm giving you what you need, that the probability of any exact value is 0. That sounds like a quiz question to me. And the probabilities are always in ranges of values. I could say 8% of those people were between 0 and 10 years old, but I can't say any given percent is any given age. Okay. Now, the normal curve is the one you are most familiar with as a probability density curve, and it's the one that we are going to be talking about. Okay. Now, a normal curve, you may or may not know, is also called a bell curve. And it looks like this. And I'm trying to draw it as symmetric as possible. In fact, I'm going to change it a little bit because I'm trying to draw it so it's exactly symmetrical. And that means that these two tails are the same. And if I drew a line right down the middle of this, it would be splitting this exactly in half. Okay. I didn't draw this with a ruler or anything, so it's not perfect, but this is supposed to be perfectly symmetrical. Now, this line right here that splits it exactly in half is the mean. And in a normal distribution, the mean, the median, and the mode are all equal. So this line right here is the mean, the median, and the mode. And from now on, we're going to call that mu, which is a capital squirrely little m, which is the Greek m, and then u. I'm just going to call it mu. Don't worry about it. Call it mean, median, and mode for now. I will call it mu. You will all be calling it mu soon. Okay? Now, in a left-skewed distribution, we're going to have a tail on the left. So it's going to look more like this. I kind of exaggerated it, but my bump is on the right and my tail is on the left. And that is called a left skew. Left skew. It's also called a negative skew. And in that case, the mean is going to be less than the median and the mode. The mean is going to be less than the median and the mode. And think about this now, why this would make sense. If you had a whole bunch of tests and all your tests were really good. Let's say you had 90, 92, 93, and 97 for your 4 test scores. And then all of a sudden you took a test and your score was only 60. You know what that would do to your average. A 60 would bring your average down. It would pull it down or negatively or to the left because the average is now going to be lower. Your average is no longer going to be in the 90s because that 60 is pulling it down. So your average is going to be over here somewhere, pulling this data to the smaller side or to the left. Exactly the opposite. If you have a bunch of low scores, maybe for you scores in the 70s are low and you're really trying to get a higher grade, but you've got 76, 75, 78, and 77 as your test scores. And then all of a sudden you take a test and you just rock it and you get 93. Well, now your average is going to be pulled up. It's going to be pulled to the right because it's no longer going to be in the 70s. That high 93 is going to pull your average this way. So now your tail is going to be on the right. And this is going to be called a positive skew. And now your mean is going to be greater than your median. Your mean is pulling it to the right, that one high score. Okay, so that is what is called skew. And we have right skew, left skew, and symmetric. And they're not always exactly symmetrical. You have to be careful about that. I mean, you use your common sense. If it looks like it's symmetric, it's supposed to be symmetric. But we also have what's called bimodal. Now, the mode is what's most common. So no matter what kind of skew I have, this, by the way, is a right skew because the tail's on the right. This has one mode because this bump has to be where the mode is. And because it's the highest, it's the most common. Now, if you happen to have 2 modes in a set of data, you could have a set of data that looks similar to this, where you have 2 big bumps. Then it would just be called bimodal. Or maybe you've got data that maybe it just sort of looks like this. And everything is sort of the same. Maybe it looks like there's 2 little blips right here, but for the most part, it's pretty uniform. You can just call it symmetric. So I'm going to make it really obvious which way it goes so that you don't have to be guessing, okay? It's going to be bimodal means 2 modes. Unimodal would mean there's uni means one mode, unimodal. Bimodal, 2 modes. There could be multiple modes, but I won't be giving you any of those. Otherwise, left skew, right skew, and normal. And there you go.